let's take a look at more about Rutherford scattering and the Bohr model. So once Rutherford inferred that there was the existence of a nucleus within an atom, he and others went further with their experiments. So remember, the Geiger-Marsden experiment, or the Rutherford experiment, or the gold-foiled experiment, whatever you call it, the big idea was that you send in these positively charged alpha particles toward a gold atom or some other metal, and to explain the results that we're seeing, Rutherford suggested this. We have an atom, and inside there is a massive positively charged nucleus. And the alpha particles, which are sent in, have a couple of different things that they can do. If they pass through the outer part of the atom, they essentially pass through nothingness, empty space, and so they just pass straight through. If they pass close to the nucleus, they get deflected, like that. And if they approach head-on, they approach the nucleus, and then they bounce back the way they came. And the behavior of alpha particles in this way is called Rutherford scattering. So consider what happens when we send in an alpha particle directly toward the nucleus. If that alpha particle does not have very much kinetic energy, then it's not going to be able to approach the nucleus very closely. But if we send in a higher energy alpha particle, it will get a little bit closer. And if we send in an even higher kinetic energy alpha particle, it'll get even closer to the nucleus. So what happens if we send in an alpha particle with so much kinetic energy that it actually touches the nucleus, whatever that means? Well, in that case, we no longer get Rutherford scattering. We no longer get Rutherford scattering because essentially the alpha particle enters the nucleus. It's no longer deflected like it was before. It actually gets into the nucleus, and nuclear forces become important. Now, we haven't learned about nuclear forces, but there's things like the strong nuclear force and the weak nuclear force, and those forces affect the motion of the alpha. So it's not just the electric repulsion that's going to affect the motion of the alpha, it's these other nuclear forces, and in that case, we won't get Rutherford scattering anymore. So scientists used this idea to estimate the radius of the nucleus, and it went like this. Assume we have a head-on collision just for simplicity, and we're going to draw the nucleus right there, and we're going to have an incoming alpha particle. Let's imagine that we're trying to calculate the radius of closest approach. So that's the closest distance that the alpha particle gets to the center of the nucleus. And we're going to calculate that using energy conservation. So the energy of the alpha particle at the beginning is equal to the energy at the end. The energy at the beginning is all kinetic energy, right? This alpha particle is coming in with some amount of kinetic energy. And the energy at the end is the electric potential energy. It does not have any kinetic energy right here at the moment of closest approach, because that's the moment when it turns around. That's the moment when its velocity is zero, its kinetic energy is zero. So the only type of energy it has in the end is electric potential energy. So we'll write this expression. I'm going to write down the initial kinetic energy of the alpha particle as E alpha. And then the electric potential energy at the end is given by this expression, K Q1 Q2 over R. Those two Q's, well, one of the Q's is the charge on the alpha particle, which is 2 times the elementary charge. And one of the Q's is the charge on this nucleus, which is however many protons we have times the elementary charge. And the number of protons in the nucleus we're going to represent with the letter capital E. So now we have this, okay? The energy of the alpha particle initially is equal to 2kz e squared over r. And if I solve for r, the distance of closest approach, I get this expression. 2kz e squared over the energy of the alpha particle. So now we have an expression for the closest that an alpha particle can get to a nucleus based on the charge on the nucleus and the charge on the alpha particle and the initial energy of the alpha particle. So here's what they did. They would send in, say, one alpha particle with a certain amount of energy. And the distance of closest approach for this they would calculate to be, say, 8 femtometers. So they send it in, and let's say that they observe that they get Rutherford scattering in that situation. So it behaves like Rutherford scattering, which means that it did not enter the nucleus. And then they send in an alpha particle with more energy, where its distance of closest approach would be 7.5 femtometers. And let's say they do that, and they get Rutherford scattering again. And then they send in a third alpha particle, and it has more energy, and so its distance of closest approach is 7 femtometers. And in that situation, they observe they don't get Rutherford scattering anymore. Here is the explanation for that. In the first situation, with that low energy alpha, it got close to the nucleus, but didn't get in. In that second one, they still saw Rutherford scattering, so it got close to the nucleus, but it didn't go in. The third one, it was no longer Rutherford scattering, and so in that situation, it did enter the nucleus, which tells us that the radius of the nucleus is somewhere between these two radii. The radius of the nucleus is somewhere between 7 femtometers and 7.5 femtometers. And so that's how you can estimate the radius of the nucleus. And they did this for many different nuclides, and it turns out that there's a pattern. The radius of the nucleus varies with the number of nucleons, which we will represent with a capital letter A, like this. It's proportional to the number of nucleons to the 1/3 power. Or if we were to plot the radius of the nucleus against number of nucleons to the 1/3 power, we'd get a linear graph. So that means that the radius of the nucleus is proportional to the number of nucleons to the 1/3 power. We can turn this into an equation by adding a constant. So the radius of the nucleus is equal to some constant times the number of nucleons to the 1/3 power. And this expression is in your data booklet. That constant, R0, is called the Fermi radius, named after Enrico Fermi. And the Fermi radius is equal to 1.20 times 10 to the minus 15 meters. That value is given in your data booklet. So now that we have an expression for the radius of a nucleus, we can get an expression for the density of the nucleus. So let's see, density of a nucleus, that's equal to its mass divided by its volume. Well, the mass of a nucleus is approximately the nucleon number times the unified atomic mass unit, because every nucleon has approximately 1 U in mass. Not exactly, so this is an approximation, but it's a pretty good one. The volume of a nucleus, well, we'll assume that a nucleus is a sphere, so the volume is 4/3 pi r cubed. If we insert our equation that we just got, well, let's see, we have AU over 4/3 pi times Fermi radius A to the 1/3 on all that to the 3rd power. Distribute the cubed, and okay, we got that. And you see, the nucleon number cancels out, and so we get that the density is approximately U over 4/3 pi Fermi radius cubed. If we simplify that, it's 3U over 4 pi Fermi radius cubed. And if you put in all the values and calculate it, you get that the density of the nucleus is approximately 2.4 times 10 to the 17 kilograms per cubic meter, which is an absolutely huge density. Nuclei have very, very, very high densities. And the other thing to point out is that the density is independent of the nucleon number. No matter how many nucleons you have, the nucleus always has approximately the same density, whether it's uranium-235 or lithium-7. So now let's move on to the Bohr model. And when we think about the Bohr model, we're going to focus a lot on hydrogen. The reason why is because it's the simplest atom. It has 1 proton and 1 electron. Maybe some neutrons, but don't worry about them. So when Bohr was developing his model, this was when people knew about the nature of the nucleus, but they did not understand spectral lines. They did not understand why spectral lines were what they were. They had observed that all atoms have unique spectral lines, in that they emit and absorb only very specific and unique wavelengths or frequencies or photon energies. But it was not explained why these spectral lines were what they were. However, people did notice a strange pattern for hydrogen. It was observed that the photon energies were always differences between negative 13.6 eV over n squared. No one had a good explanation for why that was until Bohr proposed his model. And when Bohr proposed his model, he said that there are only certain allowed electron energy levels in an atom. He called these stationary states, which is a little confusing. It doesn't mean that the electron is at rest. The electron is not stationary, just that its energy is fixed. And he also said that when the electron was in this stationary state, it was stable. And also, for the electron to move to another state, it had to absorb or emit a photon, which we've seen before. And then he also said this other assumption that was a little bit odd. He said that the angular momentum of the electron had to be equal to n times h over 2 pi, where n is equal to 1, 2, 3, non-negative or non-zero integer. So if you haven't seen angular momentum before, it's a momentum that's associated with circular motion, and you'll see it more when we do rotational dynamics. And it's equal to mvr. So in the data booklet, you'll see this expression, which is one of the assumptions of the Bohr model, that the angular momentum mvr must equal n times h over 2 pi, where n is a non-negative non-zero integer and h is Planck's constant. Here's the thing. If you make these assumptions, then you can go through a rather long proof, and I'm going to do it very quickly here. This is not something that you would be expected to reproduce. But at the end of the proof, if we make these assumptions, we get that the energy states for an electron in a hydrogen atom are equal to negative 13.6 electron volts over n squared, where n is that integer that is non-negative and non-zero. In other words, we get the allowed energy levels of an electron that explain the spectrum of hydrogen. So Bohr's model explains the hydrogen spectrum, which is a huge deal. Now, it turns out this can also be used to explain other spectra from ions with one electron. So for example, if we had helium, and that helium was singly ionized so that it didn't have 2 electrons, instead it only had 1 electron, the Bohr model also explains its spectrum. So Bohr's model was an enormous success in that it explained the hydrogen spectrum, and it was very heavily accepted. However, it didn't explain everything. There's still the question of why the angular momentum would only be allowed to equal nh over 2 pi. And it also didn't explain why the electron can exist only in these special stationary states. And to explain that, we have to go to quantum mechanics, and we'll explore that further later on.